Hello learners, welcome to this course on practical machine learning using Google Colab. So in this tutorial, let us continue with our discussion on fundamentals of computer vision part 7. In this tutorial, I will be discussing about a method called as thresholding, which is a very important segmentation technique. We will try to do some practical applications as well using this thresholding method. So we will be discussing about thresholding and the types of thresholding. So we have three major types. One is simple thresholding, also thresholding, and adaptive thresholding. So let us dive into Google Colab environment and try to discuss these three different methods. So thresholding is a common step in your segmentation process. So what do you mean by segmentation? Segmentation is nothing but separating the foreground object from a background of an image. So if I have some object which we need to focus or which we need to work on, then we need to separate out that object from the background. So in order to do that, we can make use of this thresholding as a basic step. So thresholding is nothing but a binarization of an image. Binarization in the sense the image will contain either a dark pixel or a white pixel. So it can take a value of 0 or 255. So this is the process to convert your grayscale image into a binary image, where the pixel takes a value either 0 or 255. So there are three types of thresholding methods. One is simple thresholding, also thresholding, and adaptive thresholding. So simple thresholding is we try to supply manually the threshold value for an image. As a programmer, we try to provide a threshold value and we try to see whether the pixel value lies above the threshold or below the threshold value. So this technique, it really works in under controlled lighting condition, where I have a high contrast between the foreground object and the background of the image. So the problem here with this simple thresholding is, it is very difficult for a programmer to decide what should be the threshold value for a particular image. And this threshold value will vary from image to image based upon its content. So it is very difficult to select a threshold value which is very optimum for that image to do the binarization process. So once we set a threshold value, we can set all the pixel intensities less than threshold to 0 and all pixel values which are greater than threshold to 255, which means I set a threshold. If my pixel intensity is less than the threshold, we set it to black pixel. If the pixel intensity is more than threshold, we set it to white pixel, which is 255. We can also apply the inverse of binarization, which means the opposite case. If the pixel value is less than threshold, we can set it to white pixel. If the pixel value is greater than threshold, we can set it to black pixel. So the opposite nature is also possible. In order to simplify the assignment of threshold to an image, we can go for another technique, also thresholding, where our computer or the processor itself is going to determine the threshold value for us for an input image. So it is more dynamic and automatically compute the optimal threshold value based upon our input image. So once we give an input image, automatically the algorithm decides what should be the threshold value for that particular image. So how it decides? Basically, it assumes our image contains two classes of pixels, the foreground pixel as well as the background pixel. So it is going to consider our image contains two major classes of pixels. One is foreground pixel and a background pixel. And it is going to compute a grayscale histogram of our pixel intensity. As we know that histogram is nothing but it gives the pixel distribution in an image. Which grayscale pixel is more in an image or which grayscale pixel is less in an image. So that type of statistics is given by this histogram. So our algorithm, it computes the grayscale histogram of our pixel intensities, and it assumes our histogram is going to be bimodal in nature, which means it is going to have two peaks. Then it is going to assign a optimum threshold value by putting a line between these two peaks. So that line determines the threshold value. So our Whatsapp method, based on the grayscale histogram, it computes an optimal threshold value T by taking into consideration that the variance between the background and foreground peaks are minimal. So for each and every image, the algorithm can compute its own threshold value depending upon the image content. So this method really works under semi-stable lighting conditions. If the image is captured under semi-stable lighting condition, then Whatsapp method is really useful. Both this simple thresholding and Whatsapp thresholding is a global thresholding method, which means we set only one threshold value for an entire image. If I have image captured under variable lighting condition or suboptimal lighting condition, where one side of the image might be exposed to light and other side may be little bit darker, or it might not have that much lighting condition. In that case, the image is captured under suboptimal condition. In that case, the simple thresholding and Whatsapp thresholding will not work to a significant effect. So in that case, we can go with this adaptive thresholding or local thresholding. So from the name itself, we can understand local thresholding means we are going to assign a threshold for a small region in an image, not a global value for an entire image. So what we do here is we break the image into smaller pieces and we assign threshold value for each pieces separately and individually. So thereby, whatever the suboptimal lighting condition is prevailing in the image, it can be nullified or it can be minimized using this adaptive thresholding method. So here it considers a small neighbors of pixel and then finds an optimum threshold value for each neighbor. So we take a small region in an image and we try to compute the threshold value for that region. Then same way, we go to the next region, compute the threshold value. So by this, what happens, for a single image itself, we will be getting multiple threshold values. Depending upon the spatial location of the region which we have selected, we will get a threshold value. So this method assumes a smaller regions of an image are more likely to have approximate illumination, uniform illumination. If I take a small region, then in that small region, this method assumes that in that small region, I am going to have a uniform lighting condition. If I take a large region, there might be a variation in the lighting condition, but if I consider a small region, then I am going to have a small uniform lighting variation. So here the problem is how to choose the size of the pixel neighborhood. What will be the right size for my pixel neighborhood, which forms a very critical aspect. So if I take a large neighborhood, then what happens? Then there will be more variation in the lighting condition. Then we are not satisfying the earlier condition. So we should select the optimum size for our thresholding process. Next important aspect is, after selecting the size of the neighborhood, what type of statistics we should apply on that neighborhood to determine the threshold value. So we have two common practice. One is either I can use an arithmetic mean or a Gaussian mean. So arithmetic mean means each pixel in the neighborhood is going to equally contribute while computing the threshold value. So the entire neighborhood is going to equally contribute for the determination of the threshold value. That is arithmetic mean. In case of Gaussian mean, the pixels which are near to the center pixel is going to contribute more to the threshold value when compared to the far away pixels from the center pixel. That is called as a Gaussian mean. The pixels farther away is going to contribute less to the overall calculation of the threshold value. So there is a general formula to compute this threshold value. So we take a mean of the intensities in a region. IL is nothing but the intensity in a local region, small region. So we take the mean value. This mean can be an arithmetic mean or a Gaussian mean. So we find the mean of intensities in the local neighborhood minus some C. So C is nothing but some constant which we use it for fine tuning our threshold value. That is how this adaptive thresholding technique works. So we have three major types of thresholding techniques: simple thresholding, Ohlson thresholding. In simple thresholding, we manually supply the threshold value. In Ohlson thresholding, the system or the algorithm automatically computes the threshold value for us depending upon the input image. In the adaptive thresholding, we divide the image into small segments, and for each segment we try to find the threshold value either using an arithmetic mean or a Gaussian mean principle. So now let us go to the program part. First let me connect to the cloud environment in a Google Colab. So you can change the hardware settings by going to Edit, Notebook Settings. Here you can select a GPU, TPU or a cloud-based CPU. So I am going to select a GPU, save, then connect. So once I press connect, it will get connected to the cloud environment. Then our program can make use of the hardware available in the cloud environment. So it is getting initialized and it got connected to the cloud environment. So now as usual, for every program what we do, we try to import the necessary packages. So from Google Colab patches, I am going to import cv2.imshow, which is used for displaying the images. From matplotlib, we can make use of this pyplot. Argument pass for providing the image during the runtime or the dataset during the runtime, we can make use of this package. CV2 is a computer vision version 2 library package which contains lot of image processing operations, and NumPy is a numerical Python library which we mainly use it for matrix computation. So these are standard set of packages which we include in most of our programs. So run the cell. Now I am going to upload an image into the Google Colab environment. So let me upload an image into the Google Colab environment, choosing a file. I will select a file. So let me select this coin file. Then I am going to read this image by using cv2.imread function. Then convert this image into a grayscale image. Right? So using this flag cv2.color_bgr to gray, which converts your color image into a grayscale image. Then I am going to blur the image using Gaussian blur function. So here I apply the grayscale image, and this is the kernel for your blurring operation, and since it is a Gaussian blur, we need to give a sigma value. So we can make the computer to predict the sigma value for us by providing 0, or we can also provide the sigma value here. So once this is done, we try to see the original image, grayscale version of the image and the blurred image. So by blurring, we lose some details, and it also helps in removing the noise from our image. So when I execute this, you can see this is the image which we are going to work on. So this is our coin image, original image, and below is the grayscale version of that image. This is the grayscale version of the image. So in a grayscale image, the pixel intensities will vary from 0 to 255. So 0 means black, 255 means white color. We can have different shades of black and white. Then we have a blurred image. So here you can see the high frequency component. So high frequency in the sense, if I have some pixel variations, that is called as a high frequency. So those component gets merged with your background. So this will help in removing the noises as well. Now let us start with our thresholding process. So first I am going to apply simple threshold. So in order to apply simple threshold, we have a function in CV2 which is CV2.threshold. So I give the blurred image, I set the threshold value. This 200 is my threshold value. So once my threshold value is set, we need to see whether the pixel intensity is greater than this threshold or less than this threshold. If it is greater than this threshold, what should be my output value? So that output value is given here. So if my pixel intensity is greater than the threshold, then it will be set with the value of 255. So we use CV2.threshold underscore binary function, which is a normal thresholding operation. If the pixel value is greater than 200, it will be set with 255. If it is less than 200, it will be set with 0. So we get two outputs. One is the threshold value and the thresholded image, the binary image we try to get as an output. So we try to plot it and see how the blurred image looks like and how the threshold image looks like, and also we try to print what is the threshold value which we have supplied to our code. So when I execute this, you can see this is the blurred image and you can find the threshold image. So let me zoom out and try to explain this. Here you see, this is my blurred image. So we have set a threshold value of 200, right? So each pixel will be compared with this 200. So if the pixel value is more than 200, it will be set to white. For example, here in this region, I have a white pixel, which means it will be greater than 200, which means I have to set it to 255. So you can see yes, 255. So inside the coin, if you see, it is less than 200. The grayscale value is less than 200, which means I need to set it to 0. So that is why the coin region looks 0 or black. And there are few white patches inside the coin region. Here you can see some small white patch. Here you can see some small white patch. Here you can see. So those regions, there the pixel value is greater than 200. So those regions are appearing as white patches. So that is how this simple thresholding technique works. So here you can see what is the simple thresholding value which we have given is 200. Next we will try to do the inverse operation. So inverse in the sense, if the pixel value is greater than threshold, we try to assign it to black. Less than threshold, we'll take a white color. So how to do that? By using this function again, CV2.threshold. We give the blurred image, threshold value, output value, and we supply a flag of threshold binary inverse. So this flag will make, if the pixel intensity is greater than threshold, it will set it to black color. If the pixel intensity is less than threshold, it will set it to white color. Again, we get a threshold value and the thresholded image. So we try to plot it and see. So now we will see the different result. Here you see, I have a blurred image, and now you can see there is a white region. Previously it was black. Okay, previously it was black. Now you can see it is white. The coin regions are white because now it is an inverse process. If the pixel intensity is greater than threshold, it will be set to black. You can see outside regions are set to black. Whereas the region inside the coin where I have the pixel intensity less than threshold is set to white in color. Now we can make use of this thresholded image to extract the region from our original image. So that we can do by applying CV2 dot bitwise AND. So CV2 dot bitwise AND of my image with the masked version of my thresholded image. When I apply AND operation, what happens? Only the region available in the white pixel will get extracted. Other regions will go to 0. Right? So only the white pixel regions in the thresholded image will get extracted. Other regions will go to 0. So when I execute this, you can see the coin region is extracted from the image. So from my original image, I have a white background. Right? I have a white background. In that I have coins. Whereas after applying this masking function, CV2.bitwise AND, we extracted the coin regions from the image. So that is how we can segment our foreground object from a background. This is an example for your simple thresholding technique. So here we are manually supplying the threshold value 200. But this threshold value may vary from an image to image. So this is not a unified or global input. So we need to change it from an image to image, and computing the threshold value will be really difficult. So in order to do that, we go for the Ocho thresholding method. So in Ocho thresholding method, again we use the same function CV2.threshold. I give the blurred image. So now we are not going to supply the threshold value. So that is the difference here. Previously we are manually supplying the threshold value. Now we are asking the algorithm to make a prediction for us. We are asking our algorithm to make a prediction of my threshold value for that input image. So we put it as 0. Okay, so I say I don't know what is the threshold value. So after computing the threshold value, the output value will be set to 255. So now I insert two flags. One is for whether I want an inverted version of my thresholded image or a normal version, and I also specify the Ocho thresholding. I am going to use Ocho thresholding to compute this threshold value. That is why we put two flags OR together. So this is the OR symbol. So I say Ocho thresholding method is used for computing the threshold value. After computing the threshold value, what type of thresholding mechanism should be taken care? Whether it should be a normal thresholding or it should be inverse thresholding. That is taken care by the CV2.threshold binary inverse. So once this is done, the algorithm will return me a threshold value which it has computed by itself automatically. We are not providing the threshold value. So this threshold value is given by the algorithm and the thresholded image. So we try to plot it and see. Then we also use the bitwise AND function to extract that region from the original image. So when I run this, you can see Ocho thresholding. So it gives this Ocho thresholding, and what is the value it has assigned? It has assigned 191 as a threshold value. Okay, 191 as a threshold value for this image. If you give some other image, this thresholding value may change depending upon the content in the image. So once I apply this thresholded image on my original image, we can extract the coin regions. So you can see this is the coin regions extracted by using the Ocho thresholding image. So these two methods, simple thresholding and Ocho thresholding, it works really well for uniform lighting conditions. If I have suboptimal lighting condition or variable lighting condition, in that case this might not work. In that case we have to go with adaptive thresholding method. So we will look at an example of an adaptive thresholding method. So I am going to take an image which is captured under suboptimal condition. So let me choose an image. Let me show you that image, how it looks like. So here you find this image, right? So here we are reading that image, converting that image to a grayscale, the same procedure which we follow earlier. Then again I am going to apply some Gaussian blur to remove any noises with a kernel value of 3 by 3, and sigma will be computed automatically. So we see all the original image, grayscale image and the blurred image. So when I execute this, you will find this is my original image. So here you can see on one side we have very good illumination, on other side I have some shadow lying on this right side portion. So it is not properly illuminated. Even in the face you can see on one side it is properly illuminated, on the other side it is not properly illuminated. So this type of image is something like it is captured at the suboptimal lighting condition. In that case, when we convert it to a grayscale, you can find it. Here also you can see a lot of bright regions on the left side, lot of dark regions on the right side, and the blurred image will look like this. Now let us apply the adaptive thresholding method on this image. So how to do adaptive thresholding method? It's very simple. We have a function cv2.adaptive threshold. I give the blurred image. Then we specify the output value. 255 is the output value. Then here I specify a flag, whether I am going to use an arithmetic mean or a Gaussian mean. As I said a little bit earlier, so we divide the image into small segments, and for each segment we are going to compute the threshold. And this threshold can be computed either using an arithmetic mean or a Gaussian mean. So arithmetic mean in the sense, all the neighborhood pixels are going to equally contribute for the computation of our threshold value, whereas in case of Gaussian mean, the faraway pixels in the neighborhood is going to contribute less to the computation of my threshold value when compared to nearby pixels. So here I am going to use an arithmetic mean. If I want to use a Gaussian mean, you can use this function cv2.adaptive underscore threshold underscore Gaussian underscore c. So this function will help in computing the Gaussian mean in a local neighborhood. So then by applying this, we will get a threshold value for each and every subregions. Then what type of scheme I should apply, whether I should get a binary image or inverse binary image. So for that we supply this flag cv2.threshold underscore binary underscore inverse. So here I specify the region. So my region is going to have 25 by 25 pixels. So each region which we select in our image is going to be 25 by 25 pixels, and this is the C value. So in our mean computation, we have the formula. Here. We have a formula to compute the threshold value. We take the mean of intensities in the local region minus C. So this C is provided here. It is something like an offset value. So this is the local region size, 25 by 25 pixels in the local region, and this is the C value. So once I give this, I will get a thresholded image. We try to plot it and see, and then use this adaptive threshold for performing the masking operation. So when I do bitwise AND with my thresholded image, we try to extract the important portion in our image. So here you see, after applying the adaptive threshold, so these are the, for each 25 by 25 pixels, it has assumed the threshold value. Then it has computed the thresholded image. So if I do normal thresholding, what happens? On the right side, most of the regions will be black, right? Whereas here in case of adaptive threshold, you can see the important region which we are working is the girl in this picture. So this I can see to some extent that I can able to gather the information of a girl. So still much more processing needs to be done in order to retrieve the girl in a better way. So when we see the masked output, you can see the major portion of the girl is visible after applying the threshold. So in this example, we have discussed about three major types of thresholding techniques: simple thresholding, Wurtzer thresholding, and adaptive thresholding. Thanks for watching. Please subscribe for more technical learning. Thank you.